I'll be talking about dualities from match-gate tensor networks. So this is recent work that I'm doing together with Jens Eisert from Berlin, Alexander Altland from Cologne, and we hope to have a paper about this on the archive within, let's give it a month. But yeah, so none of this is published yet. Okay. Oh, this guy shouldn't be there. Okay. Let me just check if the rest of the slides look okay. Yeah, they look okay. Okay. Right, so please ignore this ugly pixelated picture on the bottom right. Okay, so in my talk, I'm going to just consider one single tensor network. And I'm going to explain to you how this single tensor network can explain, can describe three completely different physical systems or physical objects. One is the partition function of a classical 2D Ising model. The next one is the correlation function of ground state wave function for a toric code with string tension. And then the last one is a free fermionic Hamiltonian. And by making use of the fact that essentially one single tensor network describes all of these three objects, we can then translate what we learn or what we already know about the Ising model to the toric code with string tension, and also compare it to what is going on in the free fermion system. Okay, so here's a brief outline of my talk. So first of all, I'm going to introduce match-gate tensor networks and match-gate tensors. Then the main part of my talk is about establishing this equivalence between the three physical systems that I just mentioned. Then I will talk a little bit about phase transitions in the latter and conclude with an outlook of other exciting things that we might be doing in the future. Okay. So what are match-gate tensor networks? So let me give you a bit of a historical context. So match gates were they came up in the in the computation of matching sums. So that's also that also explains the name. So a matching sum is a property of a graph. So if you consider a graph with weighted edges, first of all, you can define what a matching of this graph is. So to a physicist, that would just be a dimer covering. So you cover the edges, or you find a covering of edges in such a way that all the vertices are covered, but no vertex is covered twice. And then for this matching, you can compute the matching weight, which is just given by the product of all the weights of the edges that are contained in this covering. And then if you sum over all matchings, this formula over here gives you the matching sum of the graph. Now, the interesting property of this matching sum, or one interesting property of this matching sum, is that it can be calculated efficiently on a planar graph. So there's a polynomial time algorithm to perform this calculation, invented by Fisher, Castelline, and Temperley, so this FKT algorithm. But also just looking at the problem and being being all very familiar with tensor networks, you immediately will see that this computational problem is a tensor network contraction. So then the question was, if there's a polynomial time algorithm for this two-dimensional tensor network contraction, which we have seen in this conference, it is in general hard. So in general, there's not a polynomial time algorithm to contract a 2D tensor network exactly. So this brought up the question, what exactly are the types of tensors that you can put on a 2D planar graph such that the tensor network contraction can be done with the FKT method? And the answer to this question is match gates. So this is basically the definition of a match gate tensor. It's a slightly implicit definition. This property has then further been studied and been derived quite explicitly how exactly these tensors look like, and I will come to a definition in a second. But just the intuition behind this is that if you choose these tensors to be representing subgraphs in a suitable way, then your whole tensor network will again become like a matching sum computation. So it's a reasonable intuition to think of match gate tensors as some subgraphs of a tensor network, or of a graph. Okay. So now let me give you the definition that is more suitable in our context. So when I talk about a match gate tensor, I just talk about any tensor that has n indices. The bond dimension of all these indices is just 2. Match gate tensors are parity even, meaning if you have the sum of all these indices, I, j, k, etc., adding up to an odd number, the tensor entry vanishes. We will use normalized tensors, just meaning that the 0, 0, 0 entry of this tensor is set to 1. This will just make life simpler. It has no drastic consequences. And now the main property of the match gate tensor is that instead of specifying 2 to the n different entries, which you would normally have for a general tensor with n indices, you only have n over 2 or n choose 2 independent entries. And they can be associated to or they can be identified with the edge weights of this subgraph that I was talking about in the previous slide. So for example, if you have a tensor with 4 indices, this would correspond to a tiny subgraph with 4 vertices. And then these n choose 2 independent entries can be identified with the weights connecting the edges of all these vertices. On a more formula level, you can okay, so what I also like to do is to call these independent entries the second moments of the tensor, because these are the entries of the tensor where you have 2 ones and the rest of the indices are 0. So you might think of this as like a 2-point correlation function in a very loose sense. So these entries of the tensor are independent, and then all other entries are given by those second moments by a sort of Wick theorem. So how does this work? So what you do is you store all these independent entries in an antisymmetric n by n matrix. And then the higher moments, so for example, this tensor with 4 ones is given by the Pfaffian of this matrix A. Sorry. So if you had a tensor with say 6 indices, then the highest weight or the highest moment of this tensor, so the tensor with all 6 indices set to 1, would be given by this Pfaffian of A. And for example, a fourth moment where you just have 4 ones and the rest is 0 would be given by choosing a suitable submatrix and then computing the Pfaffian of this submatrix.
Do things commute or anti-commute?
This is all purely bosonic, so there are no fermions yet. I will come to fermions in a bit. Okay. So in this talk, I will only be considering these tensors with 4 indices. So everything, all the stuff that is written on the right-hand side here is already enough for you to know for this talk. Okay. Now I will make an even more drastic restriction. So I will consider match gate tensor networks that have an additional property, which is that they are factorizing. So what I mean by this is that I can write these tensors as a product of a Z2 tensor and some weight matrices. So this Z2 tensor is just a tensor which projects to even parity. So it fulfills the condition that all these indices under Z2 multiplication have to multiply out to the identity. So this already incorporates the the parity even constraint. And then the only freedom that I have is to choose weights at all the edges. So I can multiply this by a diagonal matrix, and this is really all the freedom I have. Now, not every match-gate tensor can be written in this form, but there's a particularly simple kind of match-gate tensor that can be written in this form, which is a completely homogeneous match-gate tensor. So it's a tensor where there's just one single parameter that describes this whole tensor. Let's call it A. And due to the fact that the fermion of this very simple matrix is just given by A squared, we see this factorizing property almost immediately. And the weight matrices that I should use here just take this form. So this very restricted, simple tensor is what I'm going to be using in the rest of this talk. So again, I will consider a translation invariant tensor network just defined by one single parameter, and due to this fact that it's just one single parameter, these match gates are factorizing. Note that this looks maybe similar to a PEPS, but it's not a PEPS because there are no physical open indices. So this is, yeah.
Go back to your matrix A. How does that relate to the matrix of a unitary match gate, which has this kind of even and odd parity subspaces, filled up? So you have this kind of corner elements non-zero and the inside of the 4x4 matrix non-zero. There's a determinant condition, like there's like two matrices that's whose determinants have to be equal.
I don't know.
So because unitary match gates,
yeah.
they have this different representation. I'm trying to understand how A relates to that. Matrix A relates to that.
Yes. I can't. So I think I roughly know what you mean, but I can't answer this right on the spot. And I probably, even if I could, I would like to have a blackboard for this. So yeah, sorry. So I'm really just considering this graph theoretic match gates, which came up in this context, and I know that there's a relation to unitary match gates, but yeah, I can't give it right away. Okay, so now let's take this tensor network and do what I claimed we could do. Let's just map it to the partition function of the two-dimensional Ising model. So this is relatively straightforward. Due to the fact that our tensors are factorizing, we can immediately write it in this more neat structural form. And then all we need to do really is to apply one single gauge transformation. So we just need to apply two Hadamard matrices on these bonds in the way shown here. Hadamard matrix is square to 1, so we're actually just performing a gauge transformation, nothing much is happening. And then we use the fact that under conjugation by Hadamard matrices, these Z2 group tensors transform to delta tensors. And when we apply the Hadamard transformation to our weight matrices, we obtain matrices that are now no longer diagonal, but just some general matrices. But if we look a little bit closer, we can really identify them with the transfer matrix of the Ising model. So the tensor network that we obtain after the gauge transformation has delta tensors at all the vertices, so they correspond to our Ising spins because they can only take the value 1 or 0 and put it out to their neighbors. And then these yellow matrices over here, these are the transfer matrices, so they will give a factor depending on whether the neighboring spins are up, 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 down, 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 and so on and so forth. And we can explicitly see the relation between the Ising transfer matrix and this one single parameter A that we put into our match-gate tensor network. And the identification is as follows. So we just read off that the product of interaction strength and the inverse temperature is determined by this single parameter A. Now there's one thing that I should point out. So this mapping only makes sense if we consider values of a smaller than 1, because otherwise this exponential mapping doesn't really go through. But if we are in the situation that we start with a parameter a that is larger 1, we can actually do a slightly different gauge transformation. So we can first do a rescaling of our tensor network and then actually employ the Z2 symmetry of our tensors to perform a just slightly different gauge transformation. And the result of this mapping will just send a to 1 over a. And then we can again make the identification with a classical 2D Ising model partition function. Okay, so now let's.
Can I ask, do I understand? I think I'm a bit unclear about. Oh, whoops! I'm sorry. I'm a bit unclear about the constraints on. Can you in principle consider a to be arbitrary complex number by analytic continuation? Because you can still compute it, right? Or is there some kind of a trouble? In particular, you could, in principle, analytic continue where this becomes a unitary kind of evolution.
Yeah, that is right. So I have only considered real values so far. So there's later we will see that if you choose non-real matrices, you will end up with non-Hermitian Hamiltonians, which is probably also an interesting direction to explore. I've also briefly thought about having the statistical mechanics model defined for a complex A, but I don't know enough about analytical continuations to really talk much about that. Okay, so now let's come to the second part, the toric code with string tangents. So Norbert has already explained to you in the morning what the toric code is and evoked this picture of a closed loop superposition. So in our match gate tensor network, we have essentially the same stuff going on. We have, if we identify indices in state 0 to be empty and indices in state 1 to be occupied by some string, this even parity condition in our match gate tensors will immediately give us the tensor network represented as a superposition of closed loop states. But due to the weights in our tensor network, these loop states do not come with equal weight, but their weight will depend on the length of the loop. So if in our match gate now we call our parameter t, then a loop of length L will be suppressed or enhanced by it will carry a factor t to the power of L. And usually, if we think of t being smaller than 1, that means that long loops are suppressed, and this state that we're considering is dominated by short loops. Now, as I have said before, I mean, the intuition of this is kind of right, but this is actually not a PEP. So there are, as I said, no open physical indices. So even though I see some toric code with string tangent structures there, I can't really make this mathematically precise. But I can actually do it in a second. So what I will do is I will first rewrite this tensor network again in this factorizing form. And then I will just add physical indices at the edges. So these are, again, delta tensors. So they just output the virtual index value and promote it to a physical degree of freedom. So this is indeed a ground state of a toric code where there's string tension in the system. But now the problem is that this is no longer a match gate tensor network simply because these delta tensors are not match gates. But what I can do is I can consider the correlation functions of these states instead. So I can consider a sandwich of a bra and a cat layer with some arbitrary local operator sandwiched in between. And if I do this, this object here will actually become precisely a match gate tensor network again. So if I do this double layer construction and consider a tiny tensor network patch, this will look like the following object. So we have our bra layer and in the back and the cat layer in front. And we perform the contraction over all physical indices except for maybe some points where we would like to insert our local operators. And due to the structure of these tensors being diagonal and being Z2 tensors, we actually see that this double layer of Z2 tensors reduces to a single Z2 tensor at the vertex. And the weights just pile up. So the two weight matrices of the bra and the cat layer, they emerge in a product form on these edges here. So of course, this only works for diagonal matrices. Otherwise, we would have like commutativity issues, and this whole contraction would not go through. But due to the factorizing property, this works out. And after the contraction, we are left again with a proper match gate tensor network. So this is yes.
Is there a benefit to having a match gate tensor network?
Well, I mean, match gate tensor networks are efficiently contractible. But for the purpose of this talk, I'm just establishing like exact equivalences, like dualities between different objects. And my working horse is a match gate tensor network. So I could also directly go from the 2D easing model to the toric code with string tension without going via match gates. But for me, match gates is just the easiest way to see this. Or maybe like factorizing match gates, right? So like this object here is really what I want to study and what I want to interpret as different physical objects.
Right.
Yes.
The copy tensor with 3 legs is not a match gate because it has non-zero elements for both even and odd sectors. But if you have any copy tensor with an even number of legs, it's always a match gate tensor because only even elements are non-zero.
Yes.
Okay, thanks.
Okay, so if I perform this contraction on the whole patch, these open virtual indices put out from a delta tensor, they will also get contracted with the neighboring open indices. So all I'm left with is this match gate tensor network. And the only thing that really happens is that if I start off with a string tangent T in this tensor network, after the double layer construction and the contraction, I will end up with parameter T squared in this network. And yeah, as I've said already earlier, you can derive the map between the 2-dimensional easing model partition function and the toric code with string tension without going via match gate tensor networks, and this has already been done sometime in 2008 by Claudio Castelnuovo and Claudio Chamon. When I started looking at this match gate tensor network, I was not fully aware of this result, so I found this independently, but of course, like I would like to point out that this equivalence alone is not new. Okay, so now let me move on to the free fermion Hamiltonian. So again, we consider this 2-dimensional match gate tensor network. And now I would like to remind you of the definition of the match gate tensors, because from this reduction of having 2 to the n coefficients in a tensor in general, and going to just having like an n-dimensional matrix, n times n-dimensional matrix that specifies this, you should see that there's a connection to free fermions already. Yeah.
Sorry, I think I slightly missed the point. Like, why did you need to do this doubling?
Oh, because if I just consider the toric code ground state as such, I can't identify this with a match gate tensor network. So I can't say this state is equal to the partition function of a classical 2-dimensional Ising model simply because it doesn't match the structure.
See, so the upshot is, if I calculate some expectation value in the toric code ground state, that's a match gate tensor network. Yes. It's not quite the one you started with, but it's just a simple rescaling of.
Exactly. It's just a going to a squared.
Okay, thanks.
Okay, so and indeed there is a connection to free fermions. So what you can show, or what has been shown by Bravi, is that it makes a lot of sense to define a fermionic tensor from a given match-gate tensor by associating fermionic modes to the individual indices in the way shown here. So for each index you add a Grassmann variable, and the index taking value 0 or 1 is identified with the fermionic mode being occupied or being unoccupied. So if you want to fermionize this whole two-dimensional tensor network, there are two things that you need to consider. So first of all, you need to derive the fermionic versions of your tensors, and then you also need a fermionic prescription of the contraction in the tensor network. The first prescription proceeds as I just said. So you just take the tensor and associate fermionic modes to all indices. Now, since Grassmann variables are not commuting, you need to specify the ordering of these fermionic modes. So if I just say I associate fermionic modes to the indices, this is not a well-defined map, because it depends on the order in which I associate the modes to the vertices. So what I should really do is I take a bosonic match-gate tensor. I take a bosonic match-gate tensor and an ordering of indices, and this I can identify with a fermionic tensor. Now, due to the structure of the match-gate tensor, if I just multiply out this object over here, I immediately see that it can be written as an exponential of a Grassmann bilinear, where in this bilinear form, this matrix A of the independent coefficient enters. And the way this works is you just compute it directly. So you start with a 0, 0, 0 entry having no fermions, and due to the normalization, this is just a 1. And then all the fermion parity even entries, where you have all the entries with 2 fermions present. So this gives you the second moments, and then the last object is just this fourth moment given by the Pfaffian of A. Okay, so then the other thing that we need to do if we want to write down a fermionic version of our match-gate tensor network is to define what it means to contract a fermionic, or to contract two fermionic indices. So in a usual bosonic tensor network, what you want to do is you want to insert some identity between these open indices, or project onto a maximally entangled state. This is really the same thing. And this is exactly what you also do in this fermionic formalism. So you introduce an integral over Grassmann variables and multiply with this projection. Maybe I should just say this whole thing will perform the projection onto states with both fermionic modes present and both fermionic modes absent. So this is just a consequence of how Grassmann integration works. So if you, for example, consider this first term over here, this will project onto states where to the right of this you will have exactly one θ1 and one θ2. And this object here will only project to states where there are no θ1s or θ2 present. So this is just a projection onto the both fermions are there, both fermions are not there. Right, there's one more ingredient that we need to have a well-defined fermionic tensor network, which again has to do with the fact that Grassmann variables are not commuting. So it actually makes a difference if I contract θ1 with θ2 or I contract θ2 with θ1. So just to have a well-defined assignment, I need to specify an orientation of these fermionic bonds. Okay, and at last, let me point out that this contraction can also be written as an exponential of some, in this case, very simple Grassmann bilinear. And we will make use of this fact now because what we can actually see is that this whole tensor network, if you fully contract it out, can be written as something that very much looks like a partition function of a free fermionic system. So you just end up with an integration over all fermionic modes in your system corresponding to the contracted bonds. And then in this exponential, you have a bilinear form that contains two factors. One is just the collection of all the individual matrices defining the tensors. And the other one is the signed adjacency matrix of the network. Right, and now what we do is we use...
Can you define, see, what is the what is that, the adjacency matrix?
So this matrix just has an entry 1/2 between the left mode and the right mode. So these theta vector is just a collection of all the modes in the system. So this is a very sparse matrix which has a 1 at theta n, theta m, if theta n and m are neighbors, and a -1 for theta m, theta n. Okay, so now we interpret this. So now we just look at this Hamiltonian as if it was the Hamiltonian of the single particle Hamiltonian of some free fermionic system, simply because it has the exact same structure that we encounter if we compute, like for example, any Green's functions of a free fermion system. And due to the structure of the tensor network, these I should really call them pseudo-Hamiltonians because I need the parameters of the matrices to be real to obtain Hermitian Hamiltonians. But okay, so due to the structure of my tensor network, these pseudo-Hamiltonians have a particular property, which is that they are antisymmetric. And therefore, we identify them with the Majorana form of class D superconductors. So if you have a free fermionic Hamiltonian, and this is not particle number conserving, but has no further symmetries. So you have a BDG Hamiltonian. Then there's a standard form how to write this Hamiltonian, and where you just go to a Majorana basis, and in this basis, like a general BDG Hamiltonian without further symmetries takes on exactly this form. So we identify it with a class D superconductor or insulator, and since we're in class in 2 dimensions, we would expect to find a z-value topological invariant for this Hamiltonian, and this is exactly what we are going to study next. So since we have a completely translation invariant system, we can just look at this Hamiltonian in Fourier space. So just to make a connection to the free fermionic Hamiltonian, what we should really think of is some hopping Hamiltonian, or could also be pairing, but there's the individual tensors become unit cells, and the parameter of the match-gate tensor A is identified with a hopping strength between sites in the unit cell. So this is the unit cell part of my Hamiltonian. And then the tensor network structure, this adjacency matrix, corresponds to hopping between unit cells, which is just weighted by a factor 1. So there's no free parameter in this hopping between unit cells. And if you look at this in a Fourier transformed version, then this is just a simple 4-band Hamiltonian, and you can study its band structure. Okay, so so in the generic case, you just find a band insulator, so you have the 4 bands, and there's a huge band gap between the second and the third band. So this is a plot of the Brillouin zone. But then there are also 2 particular parameters where you find a band gap closing. So for A being square root 2 minus 1, you find Dirac cones at the edges of the Brillouin zone. And then there's another critical point at A being square root 2 plus 1, where you encounter a Dirac cone in the center of the Brillouin zone. And you can write down like a single band approximation for this Hamiltonian around the critical points. And essentially, you just find a usual Haldane-Chern insulator given by determined by a mass gap and a Chern number, which you can calculate from this single parameter A in the match-gate tensors. Okay, so now let me come to the last part of this talk, where I briefly talk about the phase transitions that we deduce from having established this equivalence. So let me start with what we all know, or maybe know best, the 2-dimensional Ising model. So if we consider the magnitude of the coupling strength in this 2-dimensional Ising model measured by the product of J and beta, and we use the identification between J beta and our match-gate parameter A, we find that at the value A being equal to 1 minus square root of 2, there's a transition between a paramagnetic and a ferromagnetic phase. Now this immediately gives us a phase transition in the toric code just by this doubling mapping, where we have a transition between the trivial ferromagnet all polarized in the 0 state to the toric code phase with a fixed point at string tangent 1, and this happens at A minus square. Now, for larger string tension, we would expect a second phase transition where we end up in the trivial state, which is fully polarized in the opposite direction. So this is just the configuration dominated by extremely long loops. So basically everything is occupied. And we can find the critical string tension value for this by remembering that there's an alternative mapping to the 2D Ising model in case where our parameter A is larger than 1. So here we just end up with the identification A going to 1 over A. And just calculating this value, we immediately find that there's a second critical point at 1 plus square root of 2, so we find the other transition point as well. And then in the free fermion model, we can either by mapping to the Ising model or just by calculating the eigenvalues of a 4x4 matrix, again find the 2 critical points now for the unit cell hopping strengths in this effective pseudo-Hamiltonian, and we find a trivial insulator with a trivial Chern number below A minus. Then we find a topological region with a Chern number 1 in the intermediate region, and then we again find a trivial region. And now maybe the most interesting thing for me in this picture here is that in this case there is a straightforward connection, or maybe not so straightforward, but there is a connection between a true many-body topological phase in the toric code and a single particle topological transition in this free fermion Hamiltonian. And I mean, these 2 objects are usually said to live in completely different worlds, but with this slightly weird match-gate mapping, we can actually make a connection between the 2. Okay, so this is mostly what I wanted to say. So there are some further things to be done in the future, or some more things that have been done already. So maybe let me start with the thing that I'm most interested in the moment, which is the generalization to Zn. So everything that I've done relied heavily on this like Z2 symmetry, it's very natural to think about what happens if you go from Z2 to Zn. I think that the correlation function mapping to the statistical partition function mapping should go through, and that you should be able to find partition function of the n-state Potts model. What I'm not exactly sure about is what we end up on the free fermion side. So I think a free parafermion construction could be what is coming out there, but then also I know that parafermions are a bit more, they are more nasty than usual fermions. So I expect some trouble in this last part of the mapping. But yeah, so if anybody of you has ever tried to work with parafermions and you want to warn me about like how horrible it is, then please talk to me. So because I'm very sure I'm going to be stuck on this problem for the next half of a year or something. Okay, so there's this Zn generalization. I should also mention that similar constructions have been done where instead of taking this double layer for a correlation function, you just consider the overlap between a product state and your topological order state, and this has been studied under the name of strange correlators, and quite interesting results relating to MPO symmetry and all this stuff. So I'm also like, I want to see how exactly what I did connects to this. Okay, and then just briefly, let me just pick this 1 point out of the 3 points above, or 4 points above. It would be really interesting to study what happens if you add weakly non-Gaussian tensors. So everything here was free fermion and non-interacting in a way. But what you can do is you can add just quartic terms in your free fermionic Hamiltonian. This would correspond to like 4-body interactions in your Ising model. And since we have a mapping to this partition function of a free fermionic system, we could employ standard tools from weakly interacting topological superconductors to see how the interaction affect the properties of the system. And I would be really interesting to see if we can see like an interaction-driven phase transition on the level of the tensor network. And if the field theory that we are developing for this is actually good enough to see that. Yeah, but this is all largely open, and yeah, with that I just would like to thank you for your attention, and happy to take some questions.
Okay, we had a number, but any more questions on the floor? Tibor.
So I think you have this on this slide, but you didn't talk about it. So what would happen if I put the same tensors on a different graph other than a 2D square lattice?
So basically nothing. So if you take a regular graph, for example, like a hexagonal tiling, you would get exactly the same stuff. It's just a bit. I mean, your unit cell would be like 6 side for a triangular tensor, so it would be a bit more difficult to calculate, but nothing much would happen. People have, like Jens and Alex Jan and Fernando and Marek and so on, they have also studied different network geometries which represent hyperbolic space, so which have like negative curvature. And there you see like a dependency on the boundary correlation. So if you introduce an open boundary and measure the correlations between boundary sites, you see that this depends qualitatively on the network geometry being hyperbolic or flat, where one is a power law and the other one is exponential. But so if you look at the but there's not that much going on. So if you just look at the geodesic curves in this tensor network, you see that like like a generic power law decay will just be converted to a generic exponential decay in the transfer matrix will just be elevated to look like a power law, because the boundary distance scales with the bulk distance in a logarithmic fashion. So I mean, I started looking at this match-gate tensor networks with this holography application in mind, but actually I think because the match gates are so very restricted, there's not so much that you can say in this context. I mean, you can say a lot of things, but I don't think it's very interesting.
I guess I was wondering if there's like a 3D version of this, if I had like a 3D network.
You can definitely do 3D versions and then hopefully map to 3D classical mechanics. And maybe this is the interesting direction to go, because, I mean, establishing dualities is nice, but what I did is establishing dualities between three things that are by itself very well understood. So, I mean, of course, it makes more sense to have a duality between things where one thing is well understood and the other one isn't. Maybe 3D would exactly be the way to go.
Back in 3D, because you don't have FKT algorithms anymore.
Well, I mean, you can still map it to free fermions. So you can still, if you have a translation invariant system, you can still use the free fermion techniques for 3D. Okay. But yeah.
So the reason why you had in your model, you had a single A parameter is because of translational invariance, but that's not necessary, right? If you had different tensors on each side, you could have different alpha, different A's.
So I can definitely have a single parameter A for each tensor, but different from side to side. This is absolutely no problem. I can also go away from this uniform form condition a little bit. I can have up to three parameters, but there's a condition that these parameters need to fulfill such that the match-gate tensor is factorizing, so that I can write it with these weight matrices. This is the limiting factor. So basically, I can do everything for a tensor network where I have the freedom to choose whatever weight matrices at all these square boxes.